Hello everybody, good morning, and thank you for joining us today for our webinar and training about whirling. VARGUS whirling, our high precision system. So let's jump in. To get some motivation and to understand the market potential, so some numbers specific here from the US. We got this graph showing that we have $158 billion total US medical device market with 5.6% compound annual growth rate through 2032. Yes, today we are at, let's say, 2024 with 158 and expected to get in 2032 until $246 billion. Okay, of course, the medical device market are a lot of stuff, a lot of devices, and we are looking on cutting tools for medical application, and in this specific case about the whirling, and we here estimate a bone screw market for whirling application of about $75 million only in the US. So this is the market. Not many companies are giving solutions, and VARGUS is one of the companies to give the solution to this market. We have an example of a medical customer in the US, quite big, that is producing this kind of implants and screw that you see here. Currently, this medical customer is spending $3 million only with one competitor, and he has, in addition, $1.5 million for new screws design, ordering just now 20 plus new Swiss lathes on order, and we see that the potential is only one customer, a big one, but one customer for this kind of stuff. In this customer, we had a success. We tried on a Tsugami machine with a Fanu controller bioderm material. This is the cutting position and cutting condition that we try. And we tried VARGUS and then against the competitor, and the customer was very happy with the tool life, the surface finish, and the result that he got. And you see here, customers tested many manufacturers' whirling tools. VARGUS was the first manufacturer to make a good part in the initial testing. So we have the solution, we have a good solution, and we're ready to go to the market. So, whirling 101. Yes, we said let's make a training for the beginner, someone who never saw a whirling, doesn't know who it is. And we say it is simpler than you think. Many people are afraid from whirling. It looks complicated. They don't know how to approach it. So we'll take it step by step. These are the subjects we will cover today. How it works, catalog overview. We'll make an example in the Genius and the CNC program. As we are a virtual webinar, we cannot take you to the tech center, so we have some movies to demonstrate, to try to make it more alive. So we'll go to the tech center videos to see a setup and results of the whirling. We look on the features and benefits, and in the end we'll have some Q&A that you already sent us before, and we will address them. So let's dive in. We start with this animation of the whirling to see how it works. This is a bone screw. You see in the whirling insert, in whirling holder, in the driven tool, in a Swiss type machine. This is our system, VARGUS whirling, high precision whirling application. It's really accurate system. We run it on the most accurate machines we have. We have 3 cutting edges, various threading profiles. In our system, we have today 6 inserts that are working simultaneously. We assemble the holder in the driven tool. We can fit many different popular driven tools. We set the helix angle on the holder, and the whirling rotates, and the bar rotates and goes outside, and then we cut the thread. Ideal for long thread on small diameter components, excellent surface finish, high precision quality. We have also a double tooth solution, or even more. So in one pass for 2 starts, you see with fast machining, work holes to the spindle. You see what a nice screw you can have. So this is the VARGUS whirling, high precision whirling system. Okay, after we have watched the animation, let's see in real how it works in our tech center. So this movie is from our tech center on the Swiss type machine. Now we turn the cone of the bone screw. Here it's a end mill. We mill the flutes. Usually in bone screw we have some flutes in the edge, so the screw can enter the bone easily. And now this is the whirling. Here you see how it cuts the bone screw. Usually we work with a coolant from the back, but here we put the coolant only from the side that we can see. Here in the picture we try to show it's not so easy to see, but I want you to understand that we cut the full thread from the bar diameter. Yes, we started from diameter 6 millimeter, and we have a bone screw of a major diameter 4 and minor 1.9. And you can see how long you can cut this kind of bone screw. You see here a bit the chips. It does circle a bit because you can see how long is it. Yes, it is 100 millimeter long on a 4 millimeter major, 1.9 minor. So it's 50 times the core diameter. And here you see how long it looks, and we cut it out. And you see when you take it outside, these are the bone screw from stainless steel. You can see how nice it looks, even if it's so long. Yes, again, this is minor diameter is 1.9, major 4, so you have here 50 times the minor diameter, or 25 the major. So let's start how it works. The application is external threading in Swiss type machines. It can be a bone screw, like we see here. It can be a dental implant, or any other part that we have this application. So what are the machining options? We can do it in thread turning. We can do it in whirling, or also milling TM solid, but we'll not touch it at this point. Let's focus on the differences between the thread turning and whirling. So in thread turning, we work in multiple passes, right? We have to start 1, 2, 3, many passes until we get to the final profile. In whirling, we do it in one pass, we enter, one pass, we finish the thread. In thread turning, we have an overhang, yes, because we work in multiple passes, we have to go back and forth, and when we are in this point, so all of the legs of the screw, we have the overhang, so we'll have in long screws, we'll have more and more vibration, chattering, etc. In the whirling, it doesn't matter how long is the screw, because we are all the time working close to the spindle. Even in the example that we just saw from the tech center, in the 100 millimeter lengths, it looks like it's vibrate a bit in the end when it's very long, but still, because we are working close to the clamping, so we don't feel it. The surface finish and the look is still very nice and neat. For whirling, we do need a driven unit, which we don't need in the thread turning. This is the driven unit. Here you see the example. We brought it from our tech center. This is a driven unit. There are many kind of brands and manufacturers that produce this driven unit. We attached it to the machine, and then it transferred the movement. Here is a gear from here to rotate the whirling to cut the thread. Here we can see the angles because you need to adjust the helix angle of the application before we start. And this is how it works. We will see later on example how we assemble it, how we adjust it, but this is driven unit which is needed for the procedure. Okay, let's continue. So let's look a bit about the mechanical, the dynamic of the system. So the driven unit can move on this x-axis, on the y-axis, and also on the z-axis. Not all driven tool, not all machines can move also in the z-axis. Some yes, some not. You have to check. And also we have this arrow that we have to manually adjust the helix angle before we start. In addition, we have the bar movement, the spindle, so it can rotate on the C direction, like this, and goes out on the W direction, which is like the Z direction, but for the movement of the bar outside. Okay, so let's look on the driven tool mechanical setup. So you can see here, this is the picture from our machine in the tech center. Here is the spindle, the standard holder, coolant. And here on the side, we see the driven unit, which is not in working position right now. And here we can see it a bit bigger. And here are the angles. As we said, we calculate the helix angle before we start. We adjust it here. And then when it's time for the whirling, it will come to the spindle, cut the bone screw, and then go back to the place. Let's discuss about working points. So we have this line, which is the central line. This is the rotation axis of the driven tool by the helix angle. And then we can choose in which point theoretically we want to work. Yes, we want to work on position point number 1, 2, 3, 4, or even in between them. Yes, we said we can move the driven unit in X and Y. So theoretically we can get to any point and then start spin and work in this point. But what is important to know that we need to work on the rotation axis of driven unit, which is point 1 and 3 here, not on point 2 and not on 4 and not also in between, only 1 or 3. If we will work outside point 1 or 3, we will not get the right profile. The profile will be distorted because the helix angle and the movement, so we work on the rotation axis to keep the right profile that we designed. And we write that it depends on mechanical limitation of the machine. In some machine you cannot work, for example, on point 1, but you can on point 3, but both are okay. It only must be on this line. One remark here, in some machines, the driven tool is not vertical connected, it's connected horizontal. So the rotation axis will be horizontal. And on these machines, we will work on point 2 and 4. We will not work on 1 and 3. Yes, most important to work on the rotation axis. LZ. LZ is the distance between the rotation axis to profile center. Let's see what we mean. This is the driven tool. This is the rotation axis of the driven tool when we adjust it to the helix angle. And LZ is the line to the profile center. Yes, if we look here, we magnify it. We see this is the insert, this is the profile itself, and on the center of the profile, this is the line, and LZ is connecting between them. And let's see why is it important to know that we have this dimension LZ. Why do we care about it? So as we said before, the rotation, here how it looks, the driven tool, the bone screw that we will cut, the holder and whirling insert. Helix angle, we have the mechanical orientation. We rotate the driven unit according to helix angle of the application. Okay? So this is how it looks after the rotation. We can see it from the different views. And what that is the effect of that. After we fix the driven unit in the helix angle, the cutting edge is not centered. Yes, we have this line where that we rotate the driven tool, and in the beginning the insert is in the center. Yes, if we look here, the insert is in the center, above the center. But after we rotate it according to this line, so the insert is going out of the center. Yes, let's magnify it also to understand it more. In the beginning, the insert was here, the cutting edge, and after we rotate it, the insert moved in Ly. Okay? So if we will work like this, we will not work in the center, we will not get the right profile, the surface finish, etc. So we need to enter this correction to the machine, Ly to the driven tool, go back to the center. How do we know what is Ly? So we have a formula. Ly equals Lz times sinus beta, where beta is the helix angle. Okay, so this is why we need to know Lz. Yes, again, Lz is this distance. We multiply it by the helix angle, sinus the helix angle, and then we know what is the correction we have to enter to the machine to work in the center. So if we know that it's important to know Lz, so let's see how we can calculate it. Sometimes we can get the Lz from the supplier, but if we don't have it, we don't know it, we can check it by ourselves. It's quite simple. We'll see later on a demonstration how we did it in the tech center. But these are the steps. So first, we measure the diameter of the whirling driven tool. Parameter D. Yes, we see here, this is the driven tool. This is the arbor over here. We take a caliber, we measure it in 2 seconds, we have this dimension. Then we know that the driven tool rotation axis is the arbor center line. Yes, we have this measurement, so exactly in the middle. This is the driven tool rotation axis. Next step, measure the distance from the driven tool's rotation axis to the upper surface of the insert LZP. Okay, so we take a height gauge and we gauge this surface, and then we gauge the insert here. Yes, we're looking now for dimension LZP, and you can see the LZP is to the insert surface. So we gauge here, we have the dimension. Then we have another dimension, PDX, shows the center of the profile. You can see it here, PDX from the surface to the center of the profile of the insert. And then we can calculate LZ is LZP minus PDX. Yes, here it's easy to see it. We want to find LZ, so we have LZP from the measurement, and we subtract PDX, and we have LZ. You can find the value of PDX in the catalog. In this example, we can look on IC3V, which has a PDX value of 1.8. And we'll see the example later on, and you see that maybe it looks complicated, but actually it's quite easy. Rotation direction of the bar and the holder. So during the process, the bar moves with a rotational and an axial feed according to application parameters. Which direction should the bar rotate? Should the bar rotate in the same direction as the holder, or is it better if it rotates to the other direction. Yes, let's think that let's say that we design now a new tool. We make it a right hand or left hand, but what is the best for the performance? Should it be same direction or opposite direction? What do you think? What would you do?
Go against the inserts.
Okay. Nice guess. So actually, this is the point to remind ourselves that whirling is just thread milling. Yes, we have to think about thread milling. Okay, is external, circular on Swiss type, but end of the day is thread milling. And how do we like to work on milling? Let's remind ourselves. So on milling, we have conventional milling and we have climb milling. Yes, in conventional milling, here in this example, we have the tool rotate in this direction and the workpiece going in this direction. So we have the chip thickness begins at 0 and increase. Yes, we can see it here, On climb milling, the workpiece is going to the other direction, so the chip thickness begins at max and decreases. What are the different characteristics of this method? On conventional milling, we have the chip width increase, so the heat diffuses into the workpiece. We have more rubbing, we have chips are carried upward, and the upward forces tend to lift the workpiece. On the climb milling, we have chip width decreases, so the heat transfer more to the chip. We have less rubbing, chips are removed behind, and we have downward forces hold the workpiece down. Yes, so we have all these advantages for the climb milling, and this is why also in thread whirling we would like to work on climb milling. It's not so easy to see it, but in this in whirling, we want the holder and the bar to rotate in the same direction. This is how we achieve climb milling, and this is how we get better surface finish and better tool life. Okay, so let's have a look on a datasheet example of a driven tool. Here we have a datasheet of WTO driven tool. So what do we see here? This is the driven tool. Yes, here this is the gear to connect it to the machine. Here we assemble the whirling holder. This is from the top view. This is the holder itself with the insert. And now what I want you to pay attention to this N1 and N2. Yes, N1 is the RPM that we have here on the gear, and N2 is the RPM that the whirling holder rotates, this axis. And here on the data sheet, we see that it's not 1-to-1. Yes, in this example, it's 1.17 to 1. So, for example, if we want to work in an RPM of 1,000 RPM of the whirling holder, it means that we need N1, the gear, to rotate at 1,170 RPM. So in the CNC program, we'll see it later, we have to program S 1,170. Okay, so we need to pay attention to work on the right speed. In addition, we can see here more data like what is the maximum RPM we can work, what is the torque we can have, etc. The shaft here is 30 to attach to the machine, etc. By the way, usually this this ratio, we can see it on the driven tool itself. Okay. If, for example, on this one, you can see here the laser mark. I don't know if you can see, if the camera can zoom in. So you can see here we have the ratio N1 to N2, 117 to 1. Okay, great. Okay, let's continue. Okay, so we finished the first part, and now let's go over the second part, the catalog overview. Let's see what we have in the catalog and understand how to work with it. So this is the system that we have. We have a Swiss type machine, we need a driven unit, and we have our solution, the whirling system, the holder, and inserts. So, okay. So how do you find your tool and insert? Okay, we want to choose the right tools for the application. So there are many Swiss type machines in the market, right? Many different brands, as we see here, and each brand has different model. So first, of course, we have to recognize what is the machine and brand and model that we want to give the solution. Then there are also many driven units in the market. Also here, many brands, and each brand has different models. Not each driven unit fits each machine. Yes, you can see on the driven unit, they have different shank diameter, length, different gear. So each machine, of course, have several driven units that can fit the machine. Now we have to choose what is the driven unit that we have. Yes, maybe the customer has already driven unit. If not, he can purchase one of them. But we need to know what is the driven unit. Okay, this is important. We need to know what is the driven unit in order to choose the right whirling holder. We also have different kind of holders. Each one fits different of the driven unit. But once we know which driven unit we have, we can choose the right whirling holder. And of course, in the end, we choose the whirling insert according to application. Maybe we have standard. If not, we'll make a special insert. Let's see one simple example. So this is a page from the catalog, holder selection guide. We have here again, this is part of it, we have the machine. The machine brand and model, and the driven tool brand and model, and the whirling holder of VARGUS. We write here that it is an optional machine because it's not the most important for us to know. The most important to know is the driven tool brand and model. So let's have a look on an example. So we have a customer, we have a machine of Citizen L20, and he has a driven unit WTO 42 BJ. So very easy, we find the Citizen L20 machines in the catalog, and then we can see that they can work with different kind of driven tool, Jarvis, WTO, Madaula, WNF, but the customer has a WTO 42 BJ, and so we know that this is the right holder that we need. This is the ordering code for us. V-Whirling tool holders. So this is the tool holders we have today, standard tool holders. Of course, we make also specials. And we can see that we have different types. Yes, we have the internal, we have the bayonet, and we have the external. Let's explain what we mean between these different types. So this is the internal, Y internal. We look on the dimension D con, the diameter of connection, and we see that this is a internal dimension, internal diameter, and this red line is also for the stopper of the whirling holder. And on the external holder, we have the D con as an external diameter. Yes, external diameter, external, and also here this is the stopper. And another design is a bayonet. A bayonet, the diameter is also external, but it's a bit different. We attach each, we assemble it to the driven unit from the back of the driven unit and not from the front like these two. It comes with a device to assemble it from the back, rotate a bit, and lock it with the screw. We'll show you the example, how we do it in our tech center later on. And let's look on the Whirling full profile HA insert. So this is standard insert we have in our catalog. HA and HB are popular bone screw profiles. So we can see here the profile that we have. It could be a bit confusing. Let's see the example here of HA 1.5. For those of us who knows, for example, that ISO 1.5, it means that the pitch is 1.5. So here it is not. Here HA 1.5, it means that the major diameter is 1.5. Yes, the pitch actually here is 0.5. So anyway, you have all the data in the table. Just have a look on it. And this is the HB, similar to the HA, but this is a deep thread. The HA are more shallow. This is deep thread. Both are defined by ISO 58335. And of course, we also do specials as we do in any other applications, but here a bit more because in the bone screw, medical, in dental, a lot of the profiles are specials. Yes, many companies, many brands of dental implants or bone screw, they don't use the standard. They want to invent their own special profile to be unique in the market. So there are a lot of specials, and we do and supply these specials. So the VTX, this is the grade that we found to work best in our tech center and in tests that we've done. Very high performance, and this is the recommended grade and cutting speed that we work. In medical application, usually we work in stainless steel and in titanium. Yes, so we'll see also later on some tests that we did in stainless steel in the tech center, and this is the cutting speed parameters and speed and feed that we used. Okay, and to the next subject, we'll go to know the Genius and a CNC program example to see how it is done. So we know the VARGUS Genius that had in the past only thread turning and milling, and then we added the tapping and now also the whirling, both on the web and also on the mobile application. So let's have a look on example. Let's say we need to cut the application of HB 4.0. Yes, we saw it in the catalog. We have insert 3VW 4.0 HB VTX. We have here the parameters, major diameter of 4 mm, minor diameter 1.9, thread pitch 1.75, and thread length of 40 millimeters. Rotation axis distance, LZ. Yes, again, this is the distance between the rotation center to the profile center. We found it to be 8.1. We have a cutting diameter, this dimension, 12 millimeter, and flute count, number of flutes, in this case, number of inserts, 6 inserts working together. And we would like to work on a speed of 130 meters per minute and feed per tooth of 0.03 millimeter per tooth. So we have all these formulas in the catalog. We can calculate here what is the helix angle, the RPM of the tool, of the whirling, what is the bar feed per whirling revolution, what is the center compensation, right? We discussed about it, Ly is Lz times sinus beta. Then we have the c-axis rotation, how many degrees the bar will rotate during the whole operation, what is the tool pass, what is the c-axis feed, degrees per minute, what is the bar RPM, and what is the cutting time, how long will it take us. So if you don't want to calculate all these parameters by yourself, we can use the Genius. Let's go to the Genius. I click here. So this is our Genius. We open the Whirling calculator. I can increase it a bit, yes. So we can change the unit from millimeter to inch. We work on millimeter. So we have 4 millimeter major, 1.9 minor, 1.75 the pitch. Start, we can choose how many start. Here we have one start, and we'll work on 40 millimeter lengths. LZ, we said we have 8.1, cutting diameter of 12, and number of teeth, insert 6, insert working together. The speed is 130, and the feed per tooth, we want to work on 0.03 millimeter per tooth. And here we get already all the formulas, everything that we need, the helix angle, the LY, yes, what is the center height compensation, etc., all these numbers. And now let's see how we use this number that we got into the CNC program. Okay, so we'll copy it from here, and let's continue. So now we'll start to write the CNC program. Here we copied what we got from the Genius, but with one remark. Yes, we got from the Whirling that the Whirling should rotate at 3,448 RPM. But we remember that the driven unit doesn't transfer the movement 1-to-1, transfer 1.17 to 1. So here we multiply this number that we got by 1.17, and then we get the 4,034, which is the number we need to write in the CNC program. So this is our CNC program. This is just the beginning. Here T1010, this is the Whirling tool. And S4034, this is the RPM of spindle, including internal ratio of the driven tool, what we just calculated here. We got this number multiplied by 117, and we enter it here to the spindle. Then we go continue the machine. This is just to come before we start to work. Initial feed, and actually this is the line of the Whirling cut. That's it, only one line to cut the Whirling, the thread. So let's see. We have W40. We said 40 is the movement, the actual movement of the bar. It's going out by 40 millimeter. In the same time, it rotates at 8,229 degrees. Yes, we got it from here. See exit rotation in degrees. 8,000, etc. And it will do it in a feed, yes, of 37,436 degrees per minute. We got it from here, and we enter it here. And here we just go out from the material and finish the application. Yeah, so that's it, all the preparation, only one line to cut the Whirling. This is the speed. And you can see how we took from the Genius these three numbers, and we use it in the CNC program. So quite easy to use and have. Okay, now after we finished with the theoretical background and we understand more or less how it works, let's go to our virtual tech center and see how we did a setup, how we cut the bone screw, and what are the results that we got. Okay, so this is the first movie. This guy you see here, this is Mr. Meir Beaton. He is our tech center manager, and he helped me to demonstrate to you all the setup and everything. So thank you to Meir, and let's see here how we assemble the Whirling holder to the driven tool. Okay, now we want to show you how we assemble the Whirling holder and Whirling insert from VARGUS.
into the driven tool. So this driven tool is a bit unique. Is a WTO driven tool, and the connection mode is bayonet. It means that we don't connect it, insert. We don't enter the whirling holder from the front. We enter it from the back, and we need also a special device to do it. So now Meir will show us how it is done. So Meir takes the device, enter it from the back of the whirling holder. Now go for the back of the driven unit, enter it inside, rotate it a bit so it is stuck. Now we need to lock to tight 3 screws. Okay. And now you can pull out the device. And that's it. We are ready to go. It is fixed.
Okay, so this was the first movie. We saw how we assemble the whirling holder to the driven tool.
Oh.
And this is the second movie. We discussed a few times already in the presentation about LZ, the importance of it, and how we can measure it and calculate it manually. So let's see a video of how we did it.
Okay, so now we want to demonstrate how we can manually measure the distance between the rotation center of the driven tool to the profile center of the insert. Why is it important? We need to enter this parameter to the Genius with the parameter of the helix angle, and then we get what is the parameter that we have to correct in the setup for y, Ly, in order to work in the center of the profile in the machine. So let's see how we do it, how we measure it manually. First, we will measure this diameter of the driven tool. Then with the height gauge, we'll measure this surface at our 0. Then again with the height gauge, we will measure the surface top. Then we can calculate this distance when we know that the driven tool rotation axis is the arbor center line. Okay? What we want to find again, this is dimension LZ between the rotation center axis to the profile center. Now, what is LZP? We just have the parameter to measure the LZP between the rotation center to the profile top. And from this, we need to subtract PDX. PDX, this is the distance between the insert top to the profile center. And we know for our insert of type 3V, the PDX is 1.8. And then we can get LZ is LZP minus PDX. Okay? Now Meir will show us how we take all the measurements, and then we go back to see what we get. So now Meir is measuring the arbor diameter. Okay, Meir, what is the result? 30 millimeters, okay. Now Meir will look for the 0 on the arbor. Okay, Meir checks for the highest point to get to set the 0 at the height gauge. Okay, it's on 0. Now we can go to the insert top surface and to see what is the dimension. And what did you get, Meir? 5.11. Okay, so we have all the parameters we need. Let's go back to the screen. So first we take here the 0 on this surface. We measured with the caliber this diameter. We got 30. We know that the rotation axis is on the center, so this will be our 15. Then we measure the insert top surface, which was 5.11, 5.1. And now we want to measure LZP, which is the distance between the center line to the insert top surface. So we have to take this 15 and to subtract 5.1. So 15 minus 5.1, and we have 9.9. But this is still not the n. So we don't need LZP, we need LZ. So for LZ, we take the LZP, and we need to subtract PDX. What we said is the 1.8. So quite easy. 9.9 minus 1.8, and we have 8.1. Our LZ is 8.1, and this is the dimension. We'll enter to the Genius to see what is the correct LY we have to have to the setup.
Okay, so we just found LZ. We can calculate it. And now here in this movie, we see how we assemble the driven unit into the machine. So Meir here, adjust it here, plug it inside, adjust the angle more or less, and now lock here the 3 screws to attach it firmly. Okay, so we have the driven unit in the place. Okay, now we have a question. I'll show you a demonstration, something that happened for us in the beginning in the tech center. Let's say, let's say that now we are doing a setup for a whirling. This is the bronze screw that we want to cut, and this is our whirling holder and insert. So we know the bronze screw is coming from here, the holder is located here. So now the question is, what is the right helix direction? Yes, should it be like this, or should it be like this? Okay. So of course I can come from the top, and I say, okay, I want to work here in this in this point, on the top point, and I look from the top. I see what is the right helix. I adjust it, that it looks okay, and then okay, I said, this is how I want to work. Then suddenly we went to the machine, and we found out, oh, sorry, we cannot work in the top point. The machine cannot get there. We can only work on the bottom point over here. Okay. So now the question: should we keep the same angle, or should we change to the opposite angle? Yes, same angle or opposite? What do you think? What would you do? So it is not so easy. I think it's a bit confusing. This is why we chose also to show it. So just a second, let me open this. Okay, so this is the example I've just showed you. Yes, this is our machine. This is the bottom of the machine. This is the top. We look here. From the back, we said that we want to work on the top point. This is the screw. We want to work on the top, not on the bottom. And if I look from the top, yes, it looks Okay, right? It looks like the direction of the screw of the helix angle is the same direction as the whirling holder, so I position it correctly. But now I said, oh, wait a minute, I cannot work on this point. I need to work on the bottom point. So I just move the whirling, not to work on the top point, but to work on the bottom point of the screw. And again, I look from the top, and I say, okay, it looks good. The angle of the holder is the same as the angle of the screw itself. Yes? So actually we retried it, we worked like this, but then we saw that it was not correct. We didn't get the right profile. And then we understood, okay, it is wrong to look from the top, yes? If you are working from the bottom, so you should also look from the bottom. And when you look from the bottom, suddenly you see this picture, yes? You see that the helix angle of the holder is the opposite of from the helix angle of the screw itself. So actually you have to rotate it. Yes, so we rotate it again. We adjust, we touch on the bottom point, but we change the helix angle. So now when we look from the bottom, it looks correct. Okay, the helix angle of the whirling holder is the same as the bone screw, and this is how you work, and this is how you get the right profile and the right bone screw. Another way to look at it, because it's a bit confusing. Again, if I'm looking from the top, when I'm working, yes, this is view from the back. I'm working on this top point. So when I take the screw and I look on a drawing with the dashed lines, so now if I touch on the top point, so I work on this line, the lines that I see from the top, yes? So it's okay, I touch on these lines and I'm in the same orientation. But when I go, yes, again, view from the top, but now I go to touch to work on the bottom point. So here, if I know that I work on the bottom point, so I shouldn't look on this straight, on the full lines. I have to look on the dashed lines, and I see that the dashed lines have the opposite angle of the full lines. Yes, so actually here the dashed line where I touch, where I work, are not in the same direction as this one. This is why I know, again, I need to change the helix angle to the opposite one. Okay, now after we understood what is the right helix angle, the right direction, now let's check that we have the right and correct one. So we took this gauge on the machine. We took here 2 points. Yes, we touch in 1 point. We got the X and Z coordination. We moved along X-axis. We took another 0, and we got another X and Z axis. And from these 2 points, I'm sure all of you know how to measure the helix angle beta. We have Z, we have X. So X over here is we have here 21.276 minus 1.276. But what we need to pay attention that we have to divide it by 2. Usually in the machines, we are not working on the radius, we are working on diameter. Yes, this dimension, this parameter is of the diameter. So we have to divide it by 2 because we need to change only the change in the radius. So we get that we moved 10 millimeters. And on Z, we moved from 170 to 168. We subtract and we get to 1.88. And to find beta, we know that tangents beta equals Z divided by X. So beta is 10 degrees, 0.65. So we know we are in the accurate helix angle. One point about this accuracy, it doesn't have to be accurate at 0.01 or not even 0.1, yes? In the end of the day, the helix angle that we will get on the screw itself, it depends mainly on the program, CNC program, yes, we have on the CNC program, the rotation of the bar, how it moves out, how it spins. So this gives us the pitch itself. To position right the helix angle, it's in order to get the right profile. Yes, when we design the profile, we design it to work in this orientation. So if we change it a bit, the profile will be distorted, yes, in cosinus of the distorted angle. Yes, if we don't work at 10.65, 11, so we have like the cosinus of the difference will be our distortion. But so mainly you don't have to be accurate at 0.001. It's mainly to get the right profile and to have the relief that will have enough reliefs. Okay, so after we finished everything, we can look again on the video from the start, how we cut the bone screw itself. We have the right position, right helix angle, everything, the CNC program. Here again, we see the mill of the flutes. And now here, the whirling is coming to position and working. Again, the coolant here is only from the back, so it will not, we can see nice the movie. We see here the chips going out. We see how we cut from full diameter to the major and minor in one pass, as we discussed. We see the speed of the process at 0.03 millimeter per tooth. It's a bit moved here the point because it's very, very long, 50 times the minor diameter, 25 times the major diameter, but still we saw that the surface finish, it looks very, very nice. See how long this screw is. And when we take it out from the machine, this is the bone screw we have from stainless steel. Very nice results. Checking the profile. Okay, let's see that we worked well. We did it right. So we have here another example. Again, the profile is HB 4.0, and these are the standard dimensions. Yes, we need to keep. This is the pitch, 175, major 4, minor 1.9. And let's have a look on the angles. Yes, we have here an angle of 25 degrees and an angle of 5 degrees. So we had the customers that used our insert. He produced a bone screw, and after he produced the bone screw, he put it on the projector and measured the angle that he got. So this is what he told us. I put it on the projector and I got here not 25, I got 26 degrees, which is okay, it's close, but even here I didn't get 5 degrees, I got 10 degrees, which is really, really bad. So your inserts are not good, please correct them. So maybe you can think for yourself what was the problem. Why didn't he get the dimension, the angles, as is in the standard? So let's see what we did here. So again, this is the standard dimension. We took here the SolidWorks 3D model, and we said if we look from the top, what are the dimensions we expect to see? So actually here we see 26.5, which is not 25. And here not 5 degrees, but 9.1 degrees. Okay, so already here we see that even in theoretic form, it's not the right degrees. when we do a cross-section, yes, over here, so on the cross-section, we see the correct angles, yes, 25 and 5, exactly as it's supposed to be. And we remind ourselves when we design the insert and any thread profile, we need to check it on a cross section. Yes, either we can have a profilometer to one on it, or we have gauges. But if we want to work with a projector, we need to check the cross section. Yes, in the bone screws we have usually a high helix angle. So the higher the helix angle, the more distorted are the angles, and you will not see it when you look from the top on the full body. We check this example. We took the bone screws we cut in the tech center, and we cut them here in the middle, so we can measure the real cross section. And again, we try to measure first in the full body part. So first we see that not both lines are in focus, right? Because they are not in the same height, not the same surface. So if we focus here, so we get to 26.5 degrees, as we expect. And if we focus on the second line, we get 9.5 degrees, as we expect from the theoretical. And when we look on the cross section, so all of it is in focus because it's the same height. And here we do see the correct angle of 25.1 versus 25, and 5.05 as 5. So we do have the right and correct profile. Play with the feed. Okay, I want to give you some feeling, how it looks, how it sounds from the tech center, so like you are in our tech center. So we took this HB4. We have a material of stainless steel 316L, length of 40 millimeter, or the inch dimension here. We work in 130 meters per minute. And we wanted to check what are the differences in the different feeds. Yes, we tried 0.01 millimeter per tooth, 0.03 millimeter per tooth, and 0.06. And here the same in inch per tooth. And already from the theoretical, we see that the time, of course, is different from about 40 seconds to 13, so to 6.6. And let's see how it feels. This is our machine and our setup guy. And let's hear it. So this is now start to work. The whirling is here. You can hear the noise of working in 0.01. You can see how long does it take us, 40 seconds to complete the whirling operation. Okay? Now let's move on to the second one. Let's see how it sounds when we work at 0.03. Okay, so we hear the noise. It takes faster, 13 seconds. And now remember the noise, and let's see how it looks and feels on 0.06. The whirling is here and it's working. So we feel the sound and we see how fast we can make this thread in 6.6 seconds. Okay, let's have a look on the visual inspection, how it looks. Usually many customers, they don't check RA or RZ, they just look visual, that it looks okay, visual, all unique. And let's see what we got. So this is the screw at 0.01, 0.03, and 0.06. This is the full screw. And here in the microscope, We wanted to see the surface finish, how it seems, and let's zoom in. So now here we zoom in. We see here the step of 0.01, 0.03, and here the 0.06. We see the facets. It's a bit different than standard milling. Remember that we have the circular pass of the whirling working on a screw, a rod. So this is the dynamics, the mechanical, dynamical move that we have, and this is what we see here. But all of them actually look good and ready to go for the customer. So what are the feature and benefits we have from the system? So our VARGUS whirling, we work in VTX grade, multi-purpose grade for exotic materials. We have indexable insert with 3 cutting edge and various threading profiles. We have the single tooth solution and also double tooth solution for 2-start threading. We can make also 3 and 4 if necessary, everything that fits the insert in one pass. We have standard holder that fits popular driven tool holders on Swiss type machine. Whirling, it's ideal solution for long threads on small diameter components. As we see here, we work close to the spindle, so no bending, no vibration, no chatter, excellent surface finish, and fast machining. And of course, most important, we have the VARGUS threading quality. Everybody knows that VARGUS is known in the market as the leader in threading. We have over 60 years of knowledge, of experience in threading, how to design it, how to grind it. So all the knowledge, of course, we bring also to the VARGUS whirling, and the customers, of course, can feel it. Okay, some Q&A. Let's see what we got. So this is some question that we got in advance. So let's go over them. First question: what question do we need to ask the customer if we are going to quote a whirling? So first we have in our CMS portal, we can choose application of whirling. And in the beginning, we need all the material, like, you know, in every special, doesn't matter if it's whirling or turning and on milling. We know that it's external. We need to know right hand or left hand. What is major diameter? What is the pitch, millimeter or TPI, thread length? If there is a standard or tolerance class, is optional. It's not mandatory. Number of starts, it's mandatory. Optional material, hardness, coolant, and of course a drawing. Every time we have a special profile, we need to get the drawing of the profile so we can design it correct. In addition to this data, what else we need? So the machine manufacturer and machine type. It's not mandatory, but it's optional. But what is mandatory, we need to know the driven tool, the manufacturer, and type. Yes, as we said in the beginning, we must know it in order to see that we have the right whirling holder, or if we need to design a new one. And in addition, we will need to know what is the bar diameter, because usually we cut from the bar diameter to the thread, the final thread. And we need to know if we want a full or partial profile. Usually, customer wants, and we recommend to work in full profile, because this is the main advantage of whirling. We do it in one pass. We have the good clamping. If you make a partial profile, it means you have to cut it the major before, so you don't have a good clamping, or you do it after. So you lose the clamping, and you lose some of the advantages of whirling. It's possible, but usually we'll go for the full profile. Thicker insert sourcing for coarse pitches and multi-start threads. So this is the system we have right now. This is a small screw that we have. So today, the maximum width we have in our insert is 4.3 millimeter. So of course, we need a little bit of space on the side, so we can cut, let's say, a maximum profile width of 4. In this 4 millimeter, we can have a single tooth, double tooth, 3, but everything needs to get into 4. Otherwise, we need to make it in different passes, and again, we lose to do it in one pass. And I believe that in 4 months, we'll have the new blanks that we can already work, also have design and produce a profile width of 8 millimeters. So this is coming soon. Another point I wanted to spot here, again, about the partial versus the full profile insert. Again, I look at this example. This is the whirling. This is a screw we want to cut. And I want to notice example between partial thread and full profile thread. Let's magnify it a bit to see the differences. So actually, we had lately also some misunderstanding with a customer. We got this drawing. We thought that the customer would like to have a partial profile. So we designed it and sent to him, but at the end of the day, he actually wanted a full profile, as usually customer want. So this is why it's important to say if you want a partial or full profile, but also to understand here, when you see here a bone screw like with sharp edges here, so it's not something that you really can make with a full profile. Yes? Here with a partial profile, okay, it's no problem. We cut here the tooth, but the profile goes out and we don't touch the corner. Also here, if it's the double teeth, also here we don't touch the corner. We go over and to the next one. If we do want to cut a full profile, yes, that it means we need to make also the corner. And we cannot make a sharp corner. Yes, I have to think that we need to grind this insert in one way or another. So when you grind an insert, you must have a radius. So the minimum radius we are having is 0.05 millimeter. Yes, both here between teeth, or if it's one tooth, or also on the shoulders. Here you must have a small radius, and here. Usually, from my experience, customer they don't check it. Some of them, even if they think they have like a sharp corner, it's not really sharp. And many times also after that, the bone screws go to some chemical process or sandblasting. So anyway, you increase these edges. You don't have a sharp corner. You have some radiuses. Okay, let's look on the next question. Sign print to chip. Either any way we can shorten the delivery times. So for the process, for the design of the profile, we do have Mr. Alex Orlov now responsible in the engineering team R&D for all the specials. So he gave a very fast solution design of the profile of the insert, and then of course we go to the production. If customer already have a holder, so it's easier. We have a standard holder many times, so it's only to produce the insert. Here we still need to find some way how we can even make it faster, and I hope we will find some solution in the near future. Updated literature and online whirling videos available for customer and distributors. So we do have now this training, this video that is available for you, and we will send it to everybody so you can work with it, and we will keep adding. We'll update the catalog and also on our website and web shop. Online format for end user to upload whirling data to streamline data sharing. So what we have now is the CMS, as we just showed. You just have to enter here the data of the profile, the driven tool, a bar diameter, and that's it. We can design the profile. Maybe Ori can go over how to input in the data from the print to the VARGUS Genius whirling. So actually we just did this example during this training. 7, can Swiss machines be retrofitted with whirling heads? So I guess it depends specific on the machine. Each Swiss machine you want to retrofit, you have to check with the manufacturer. Usually, if customers are ordering a new machine, so either it comes with already with this possible of whirling, this live head, or either we can add it, or if not, if we can add it later on. I would guess that mainly you need to check that there is physically enough space to put it, the live head, the motor for that, and it should be possible to work with it. But if you need some help to check, we can help you, if you have specific question. Can we get single-page machine-specific whirling product flyers? Yes, we can work on something, I guess, based on this training. We'll try to put something in. If you have a specific request you want to include, please let me know, send me, and we'll include it before we publish it. Okay, so we come to the end finally, whirling 101. Now you are already experts. It's simpler than you think. So what have we done today? We went over whirling, how it works. We saw the catalog, we went overview. We saw the Genius, an example, how to use the Genius to write a CNC program. We went to the virtual tech center and saw how we are making a setup and what are the results we got. We saw the features and benefits, and we answered the QA session. One word about future plans. So one point was, as I mentioned, that we're going to have seeker blanks, so we can work on seeker profiles that usually work with 2 start, 3 start, 4 start, etc. or 1 start, but a big one. And in addition, we are planning to add another blank, which will not be with 3 cutting edge, will be with 2 cutting edge, but we can assemble, we can fit in not 6 inserts together, but up to 9 and 12 inserts that can work simultaneously. It will take, it's not immediately, up to 1 year and so, but these are the plans. That's it. I hope you enjoyed. Let me know if you have any question or any support that you need, or you would like me to come for a visit to support you with some customer or project you have. And I'm sure that now with the knowledge and with this market growing, we will find more and more opportunities to support the customer to have good solutions and good applications. So thank you very much. Bye-bye.
Thank you, Ori.